Hello and welcome back to Introductory Astronomy. Today we're going to conclude Chapter 16. Now the Sun is not a quiet place. It is home to slowly changing spots larger than the Earth and vast eruptions that dwarf human imagination. All of the seemingly different forms of solar activity have one thing in common: magnetic fields. So the weather on the Sun is magnetic. Solar activity is often visible with even a small telescope, but you should be very careful if you try to observe the Sun. Sunlight is very intense, and when it enters your eye, it is absorbed and converted into thermal energy. The infrared radiation in sunlight is especially dangerous because your eyes cannot detect it. You don't sense how intense this infrared is, but it is still converted to thermal energy in your eyes and can burn and scar your retinas. Now in this picture right here, we have what is called a solar prominence. A solar prominence is composed of ionized gas trapped in a magnetic arc rising up through the photosphere and chromosphere into the lower corona. If you see prominences during a total solar eclipse, you're going to see them at the edge of the solar disk, and they're going to look pink because of the three Balmer emission lines. In frame A, we see a very large solar prominence, which was observed by UV detectors aboard the SOHO spacecraft in 2002. If you take a look at frame B, just like a phoenix rising from the solar surface, this filament of hot gas measures more than 100,000 kilometers in length. Earth could easily fit between its outstretched arms. Dark regions in this trace image have temperatures less than 20,000 Kelvin. The brightest regions are about 1,000,000 Kelvin. The ionized gas follows the solar magnetic field lines away from the Sun. Most of the gas will subsequently cool and fall back into the photosphere. Which brings me to solar flares. Solar flares rise to maximum in minutes and decay in about an hour. They occur in active regions where oppositely directed magnetic fields meet and cancel each other out in what astronomers call reconnections. Energy stored in the magnetic fields is released as short wavelength photons and as high energy photons and electrons. X-ray and UV photons reach Earth in about 8 minutes and increase ionization in our atmosphere, which can interfere with radio communications. Particles from flares reach Earth hours or days later as gusts in the solar wind, which can distort the Earth's magnetic field and disrupt navigation systems. Solar flares can also cause surges in electrical power lines and damage to Earth's satellites. So a solar flare is much more violent than a prominence. It is an explosion on the Sun's surface that sweeps across an active region in a matter of minutes, accelerating solar material to high speeds and blasting it out into space. CMEs, coronal mass ejections. Magnetic reconnections can release enough energy to blow large amounts of ionized gas outward from the corona in what we call a CME, or a coronal mass ejection. If a CME strikes the Earth, it can produce especially violent disturbances in the Earth's magnetic field. in frame A right here, if you take a look at frame A few times per week on average, a giant magnetized bubble of solar material detaches itself from the sun and rapidly escapes into space. Again, this picture right here was taken from Soho in 2002. The circles that you see there are artifacts of an imaging system designed to block out the light from the sun itself and exaggerate faint features at larger radii. If you take a look at frame B, should a coronal mass ejection encounter Earth with its magnetic field oriented opposite to our own, as illustrated, the field lines can join together, allowing high-energy particles to enter and possibly severely disrupt our planet's magnetosphere. By contrast, if the fields are oriented differently, the coronal mass ejection can slide by Earth with little effect. Now, much of the solar wind comes from coronal holes, where the magnetic field does not loop back into the sun. These open magnetic fields allow ionized gas in the corona to flow away as what we call the solar wind. The dark area in these pictures shows the coronal holes, and they can be seen in X-ray images. Now, these particular ones shown in frame A were taken by the Yoko satellite. They were taken at roughly 2-day intervals, starting at the left. Now, note the dark V-shaped coronal hole traveling from left to right, where the X-ray observations outline in dramatic detail the abnormally thin regions through which the high-speed solar wind streams forth. In frame B, you see how charged particles follow magnetic field lines that compete with gravity. When the field is trapped and loops back toward the photosphere, the particles are also trapped. Otherwise, they can escape as part of the solar wind. I put a link on the bottom right-hand corner of this slide. It's a Wikipedia link that shows a nice little animation on the Earth's magnetic field interacting with the solar wind. Solar corona. This is a beautiful picture of an active corona, and it was taken during the July 1994 eclipse near the peak of the sunspot cycle. At these times, the corona is much less regular and much more extended than at sunspot minimum. Astronomers think that coronal heating is caused by surface activity on the sun. The changing shape and size of the corona is a direct result of variations in prominence and flare activity over the course of the solar cycle. Now, does the Earth feel the effects of a 22-year solar cycle directly? Well, we see a lot of possible correlations, but the causes are not well understood. We look at the energy output, and it doesn't vary very much, but we do think there's some kind of relationship, especially when we look at the magnetic field lines. We do know that solar flares and coronal mass ejections ionize the atmosphere, and this results in electronic disruptions and endangerment of astronauts or anything else that is in their path. So what I did, I put in a link to the NASA website, and it talks a lot about space radiation and how astronauts are protected from that when they're out in space. So check it out. So these are some of the things that are happening on the surface of the sun. Let's take a look at what's taking place inside the sun. Now, the sun is a very, very, very big object. Given its mass and energy production, we find that on the average, every kilogram of the sun produces about 0.2 milliwatts of energy. Remember, milli corresponds to 1,000th, or 10 to the minus 3. That's not much. Gerbils could do better. But this amount of energy production continues through 10 billion years. So it lasts for a very long time. The total lifetime energy output of our sun is about 3 times 10 to the 13 joules per kilogram. That's a lot of energy, and it is produced in a steady rate. Doesn't just happen automatically or explosively. So a good question would be, how is this energy produced? It's a lot of energy, and it's produced for 10 billion years. And the answer to that is nuclear fusion. Now, before I talk about nuclear fusion, I want to talk a little bit about the fundamental forces that govern our universe. Now, physicists recognize 4 fundamental forces. The first one, you're pretty familiar with that. We went over that on chapter 2, and that is the force of gravity. It is very weak, but it is always attractive, and it has an infinite range. The second one is called electromagnetic. It is a lot stronger than the force of gravity, but it can be either attractive or repulsive, and it also has an infinite range. The third one is called the weak nuclear force. It is responsible for a type of decay that we call the beta decay. It has a very short range, 1 to 2 proton in diameter, so you know it will be taking place within the nucleus of an atom, and it is very weak. And the last one is called the strong nuclear force. The strong nuclear force is very important because it is what keeps the nucleus together. So it also has a very short range, but it is very, very strong. Now, the strong nuclear force should answer the question that some of you may had when we were going over the atom, and we said that the nucleus is made out of protons and neutrons. And protons are all positively charged, and neutrons have no charge associated with them. So a nucleus is a small ball of matter that's all positively charged, and we know that similar charges repel. So these protons should not have been able to stay close together and form a nucleus, but they do. And the reason they do that is because of the strong nuclear force. It is what keeps the nucleus together, what keeps those protons from flying apart away from each other. Which brings me to what produces the energy inside the sun, which is nuclear fusion. In general terms, nuclear fusion works like this. You have one type of nucleus and another type of nucleus. You bring them close together in what's called fusion process, and they fuse into something else, and you end up getting a third type of nucleus out and some leftover energy. Now the question is, where does this leftover energy come from once we combine two nuclei together? And it comes from the mass. If you add up the masses of the initial nuclei, mass of nucleus 1 and mass of nucleus 2, you will find that the result is more than the mass of nucleus 3. So so that extra mass gets converted to energy. And this should be familiar to most of you. The relationship between energy and mass is given by Einstein's famous equation, E equals mc squared. Now you should be able to recognize that capital E stands for energy, little m stands for mass, and it's measured in kilograms, and little c is the special speed limit of the universe, which is the speed of light, and it is 300 million meters per second. So make sure you use the right units in order to get energy out in joules. Now notice how speed of light is a very large number. Therefore, the energy that you get out on the left side of the equation must also be a very large number. What this equation is telling us is that even a small amount of mass is equivalent to a large amount of energy. Tapping into that energy is how the sun keeps shining for so long, for 10 billion years. Now, nuclear fusion requires that like-charged nuclei, so positively charged nuclei, get close enough to each other to fuse. In frame A, they show you how something that has similar charge, two protons for example, they come close and then they get repelled and they move away from each other in the direction of the arrows. So how do we avoid this situation? Well, if we have temperatures that are very, very high, let's say 10 million Kelvin, this barrier can be overcome and the protons can fuse together. And in this picture right here in frame B, you can see how two protons can fuse into what we call a deuteron. In order for that to happen, we need to have protons that are traveling at sufficiently high speed. And they travel at sufficiently high speed when there's a lot of temperature. Once that happens, they can succeed in overcoming their mutual repulsion, and they approach close enough for the strong force to take over and bind them together. When that takes place, they will collide violently, triggering nuclear fusion, which is what ultimately powers the sun. This image right here depicts the proton-proton fusion we just talked about. Notice how we have a proton and a proton fusing together, and we have three products coming out. The deuteron I mentioned in the previous slide, also a positron, and a positron is an electron that is positively charged, and also a neutrino. A neutrino is related to the electron but has no charge and very, very, very little mass, if any. Now, if I were to write this fusion equation in terms of conventional notation, I would write it like this: hydrogen 1 plus hydrogen 1. Because remember, hydrogen, the simplest atomic element, has only one proton and nothing else. So we're looking at, when you think of proton, think of hydrogen 1. So we have on the left side of the equation two hydrogen 1s fusing together, adding together, combining together. And what we get out of it is hydrogen 2, or a deuteron, which is an isotope of hydrogen. It's an isotope of hydrogen because the neutron number has changed. It went from having no neutrons to having a single neutron. We also have a positron, which is a positive electron, and a neutrino coming out of this equation. Now, this is what we call a proton-proton chain reaction. This chain is a series of 3 nuclear reactions that build a helium nucleus by adding together protons. Now, this proton-proton chain can only happen at temperatures above 4 million Kelvin, and it becomes very efficient above 10 million Kelvin. The sun makes over 90% of its energy in this way. So here's a nice schematic of solar fusion in the proton-proton chain. So we have a total of 6 protons and 2 electrons that are converted into 2 protons, 1 helium-4 nucleus, and 2 neutrinos. The 2 leftover protons are available as fuel for new proton-proton reactions. So the net effect is that 4 protons are fused to form 1 helium-4 nucleus. Energy in the form of gamma rays, so electromagnetic radiation, is produced at each stage. Now, most of these photons are omitted for clarity. The 3 stages are indicated correspond to reactions 1, 2, and 3 that are described in detail in the text. So I definitely recommend you study this diagram very carefully and read the text. This is a very, very important chapter 16 chain reaction. If we write the second step in a form of a conventional notation, in a form of nuclear equation, it will look like this. Hydrogen 2, again the isotope of hydrogen, plus hydrogen 1 is going to fuse together and give us helium 3, which is an isotope of helium, plus the extra energy we talked about. The final step, step 3, fuses 2 helium-3 isotopes and gives out a helium-4 plus 2 protons plus some extra energy. So that is the end result. We start with 2 hydrogen 1s, we go through the 3 nuclear steps, and in the end we come out with a helium-4, 2 hydrogen 1 plus energy. Now, this helium that's being produced stays in the core. The energy that gets released is in the form of gamma rays, which gradually lose their energy as they travel out from the core through all the layers of the sun. They eventually emerge out as visible light in the photosphere. The neutrinos themselves escape without interacting. Now, the energy created in the whole reaction can be calculated by the difference in mass between the initial particles and the final ones. For each and every interaction, it turns out to be 4.3 times 10 to the minus 12 joules. This translates to 6.4 times 10 to the 14 joules per kilogram of hydrogen. So the sun must convert 4.3 million tons of matter into energy every second. Wow. It might sound as if the sun is losing mass at the Furie's rate, but in its entire 10 billion year lifetime, the sun will convert less than 0.07% of its mass into energy. Now, it is a common misconception that nuclear fusion in the sun is tremendously powerful. After all, the fusion of a milligram of hydrogen, roughly the mass of a match head, produces as much energy as burning 30 gallons of gasoline. However, at any one time, only a tiny fraction of the hydrogen atoms are fusing into helium, and the nuclear reactions in the sun are spread through a large volume in its core. Any single gram of matter produces only little energy. For example, a person of normal mass eating a normal diet produces about 4,000 times more heat per gram than the matter in the core of the sun. Gram for gram, we're a much better heat producer than the sun. Now, the sun produces a lot of energy because it contains a lot of grams of matter in its core. Fusion reactions can occur only when the nuclei of two atoms get very close to each other. Because atomic nuclei carry positive charges, they repel each other with an electrostatic force, which is called the Coulomb force. In general, physicists refer to this repulsion between nuclei as the Coulomb barrier. To overcome this barrier and get close together, atomic nuclei must collide violently. Now, this violent collision takes place when the gas is very, very, very hot, which makes the nuclei move at high enough speeds. So I want you to keep that in mind. Now, because of the dependence of nuclear reactions on particle collisions, the reactions in the sun take place only near the center, where the gas is hot and very dense. A high temperature ensures that collisions between nuclei are violent, and a high density ensures that there are enough collisions. If you have enough collisions, then you make a lot of energy, and you make a lot of energy at the rate that we mentioned before, which is 6.4 times 10 to the 14 joules per kilogram of hydrogen. Now, our sun has been fusing hydrogen into helium for 5 billion years, so it has 5 more billion years to go. In terms of numbers, and just to give you an idea, and I won't have you calculate this in the class, but just to keep in mind, the mass of the 4 protons that are needed to fuse into helium is 6.6943 times 10 to the minus 27 kilograms. The mass of the helium nucleus that is produced in the end of the 3-step nuclear process is 6.6466 times 10 to the minus 27 kilograms. So you see that difference is very, very small. And that difference in mass is what is transformed to energy, which is 0.0477 times 10 to the minus 27 kilograms, about 0.71% of the original mass. Now, the energy equivalent to that mass using Einstein's equation is 4.28 times 10 to the minus 12 joules. And you can use that to calculate the energy produced for a kilogram of hydrogen to be fused into helium, and that energy produced is a lot, 6.4 times 10 to the 14 joules. Now, it took over 30 years, but eventually physicists were able to build better detectors, and they discovered that neutrinos, the byproducts of nuclear fusion, can oscillate among 3 different types, which we call flavors. Nuclear reactions in the sun produce only one flavor. So these neutrinos are emitted directly from the core of the sun, and like we mentioned before, they'll go through all the layers and escape because they barely interact with anything. So being able to observe these neutrinos would give us a direct picture of what is happening in the core during nuclear fusion. Now, because they go virtually through everything, they're very, very hard to detect, which is why it took us 30 years to figure out that they come in 3 different flavors, 3 different types. The only way to spot neutrinos is to have a huge detector volume and to be able to observe single interaction events. Here are some typical solar neutrino detectors, and in frame A, you see a swimming pool-sized neutrino telescope that is buried beneath a mountain near Tokyo, Japan. It is called the Super Kamiokande, and it is filled with 50,000 tons of purified water and contains 13,000 individual light detectors. And their job is to detect, to sense the signature, even though it's very brief, of a neutrino passing through the apparatus. So they're trying to detect a brief burst of light. In frame B, you see the SNO observatory, or the Sudbury Neutrino Observatory, which is situated 2 kilometers underground in Ontario, Canada. The SNO detector is similar in design to the Kamiokande device, but instead it uses heavy water, which is hydrogen replaced by deuterium, and they added 2 tons of salt, which makes it more sensitive to other neutrino types. This particular device contains 10,000 light-sensitive detectors arranged on the inside of the large sphere shown in the picture. There's also a Davis solar neutrino experiment which used cleaning fluid and could detect only one of the 3 flavors of neutrinos. So this Davis experiment was designed to detect just one flavor. And during the 8-minute journey of the neutrinos from the sun's core to the Earth, they oscillated so much that they were evenly distributed among the 3 possible different flavors. So by the time they arrived to Earth, they had changed into different forms. That's why the Davis experiment and the other detectors were only able to detect only a third of the amount of neutrinos predicted based on the nuclear fusion equation. So solar detection of neutrinos is still taking place. We're still waiting to observe as many as we can. So it's an ongoing place of research. And the latest numbers that came out of solar neutrino research showed that everything is okay in terms of how many neutrinos the standard solar model it predicts. And the only problem was with the 1/3 of the amount that we were seeing before was due to the 3 different types of flavors of neutrino. So far, based on the numbers that we're seeing, the standard solar model is correct. This covers chapter 16. There's a few things you need to keep in mind. You need to be able to identify the regions of the sun. So we start with the core, then we have the radiation zone, followed by the convection zone, then the photosphere, the chromosphere, the transition region, and finally the corona. And then we have the solar wind. Energy from the sun comes from nuclear fusion. Now, a lot of neutrinos are being produced along with the energy that comes during the nuclear fusion process. The standard solar model is based on the hydrostatic equilibrium of the sun, the idea of outward pressure balancing out the inward force of gravity. Studying solar oscillations with the Doppler shift that we talked about leads to information about the interior of the sun. Using the absorption lines, we can figure out what the sun is made of, what kind of elements, and what is its temperature. Sunspots and all sorts of activity on the sun is associated with the magnetic field lines. Remember, the number of sunspots varies in an 11-year cycle. In terms of more violent solar events, we have prominences, flares, and the CMEs, the coronal mass ejections. And we also now know that the deficit that we thought existed in the solar neutrino number can be explained to the fact that there's 3 different types of neutrinos. So study chapters 16.5 through 16.8. Be able to describe the variety of solar activity and its relation to solar magnetism. You need to be able to explain the process, the 3-step nuclear process, by which energy is produced in the sun's interior. Until next time.